The three figures of the plane: the triangle, the circle, and the square. Remember? In 2500 BC, the pharaoh dreams of one of the wonders of the world, and through the creative line of the architect, the triangle becomes a pyramid, which is then repeated and redrawn throughout antiquity, the modern period, and the contemporary one. And now the circle, a line whose points are equidistant from the center. Observe its simplicity. It draws a Ferris wheel, which becomes a landmark of the City of London, a huge mirrored cookie in Abu Dhabi, and a pile of pancakes in a new library in Sydney. At last, the square. In a tri-dimensional world, the square becomes a cube or a cuboid. These are volumes that, through the ease of their representation, celerity of calculation, and of execution, they yield the most common shapes present in architecture. However, architects' imagination didn't just limit itself to the basic polygons. Over time, architecture, geometry, and engineering weren't deprived of coming up with new shapes and setting new challenges of representation and calculation. To help us understand some fundamental curves, behold a right conical surface. This conic surface is built based on a directrix, the circle of the base, and on the geratrix lines. Let's now section it. Let's see. We position the intersecting plane. Let's start with a plane that will section all the geratrixes. We shall obtain an ellipse. If we straighten this plane, making it horizontal, we get a circle, which is a particular case of the ellipse. Let's increase the incline. The intersection with a plane parallel to two geratrixes results in a hyperbole branch. If we continue to tilt the plane till it becomes parallel with the G-line, we then obtain a parabola. A parabola is the flat curve defined as the group of points that are equidistant from a point and a line. It's quite simple actually. We come across this line in our everyday lives from shore to shore on suspended bridges in Portugal, the USA, in China. Let's now have a look at these three projects. The first, the Cathedral of Brasilia by the architect Oscar Niemeyer. It was built between 1958 and 1970, and each of the 16 reinforced concrete pillars weighs in at 90 tons. Next, we have the Sagrada Família School in Barcelona. The little building, built in 1909, is a project of the last artistic stage of the Catalan Antoni Gaudí. And finally, the Oceanarium of Valencia, finished in 2002. It was the last work of the architect Felix Candela, who died at the age of 87 without seeing it completed. So what do these three projects have in common? The answer seems blatant, doesn't it? There are no straight lines, only curved meshes, right? Wrong. Or should we say, partially wrong. Okay, let's open a parenthesis here. In 2002, the Spanish architect and engineer Santiago Calatrava inaugurates Wave, a sculpture ordered by the Medius Museum in Dallas. However, Calatrava didn't just create a common sculpture, but rather a connectic piece whose movement creates a wave. The curved surface of the wave is suggested by the synchronized movement of a series of 129 beams mathematically positioned. How does this all work? Let's check with history. Vladimir Zhukov was born in 1853 to the then Russian Empire. In 1896, Zhukov built the first structure shaped like a leaf hyperboloid, a 37-meter light steel tower sustaining a water reservoir on the top. Zhukov is considered the inventor of a family of structural shapes, the one-sheet hyperboloids of revolution. So what exactly are hyperboloids of revolution? We'll need a hyperbole which will function as a geratrix. We'll need an axis, and now the hyperbole will execute a revolution around the e-axis. Let's make use of the GeoGebra through the GI_Quadrado site to help us with the tri-dimensional simulation. The full revolution of the curve around the axis has generated what we call the one-sheet hyperboloid of revolution. And what about that initial question of ours? Is it just a curved surface, or does it contain straight lines? For each of the points of the hyperboloid, two distinct lines run through and are contained in the surface. So it's confirmed. The one-sheet hyperboloid of revolution combines the curve-shaped with a twice-ruled structure. It is now time to go back and contemplate Oscar Niemeyer's curves. Niemeyer said that what attracted him was the constraint-free and sensual curve, the curve he found in Brazil, in a sinuous river course in the waves of the ocean and in the body of the favorite woman. In Niemeyer, purity of architecture comes down to this simple gesture, a poem and a curve. In the Cathedral of Brasilia, in accordance with the concept of architecture, the shape and arrangement of the pillars represent two hands lifting towards heaven. Though while Niemeyer drew the ideal shapes which would transport the Catholic to infinity, Joaquim Cardoso, the engineer specialized in structural calculation which made the Brasilia ideas possible, pondered over the best hyperboloid which best solved both the architecture and the engineering which best resolved concept and structure. Antoni Gaudí is one of the most famous architects in the history of architecture. His work primed in the use of organic and naturalistic, which in itself set it aside from the then architectural tendencies. His first work of art, the Sagrada Familia, is still today, 135 years after its start, in progress. Gaudí had a passion and a knowledge for mathematics and geometry, which allowed him to develop new structural systems without recurring to calculations. He tested his stress models in scaled-down models, which he then applied in his work. Gaudí was the first architect to use conoids in his work. Presently, and in his honor, they are called Gaudí-ruled surfaces. Let's now explain how a conoid is geometrically generated. We shall use as the directrix a circumference D. We'll use a line segment E as an axis. And finally the line G will be the geratrix and shall lean on the axis and the directrix, moving through them and generating the conoid. Let's make a second experiment. Instead of a circumference, let's use a sinusoidal directress to generate a sinusoidal conoid, the conoid that Gaudí applied in the wall and roof geometry of the Sagrada Familia school. Felix Candela was born in Spain, but at 26 he leaves for Mexico, where he takes up double citizenship. Candela had a special talent for geometry and an oath with the attraction for surfaces called hyperbolic paraboloids, with which he frequently resolved his architecture. Candela sustained that the geometry of this surface generated the necessary rigidity to enable the construction of blades with minimum thickness, the so-called cascarones. Built in 1951, the Cosmic Rays Pavilion, a small laboratory in Mexico City, was his first work employing this surface. This membrane of concrete was only 2 centimeters thick. So what is a hyperbolic paraboloid? Well, we'll need 2 non-complanar lines, R1 and R2. Let's run a third line, G, through the other 2. Now all we have to do is move the G line at constant speed through the R1 and R2 lines, obtaining the twice-ruled surface. The hyperbolic paraboloid name is due to the fact that it has both hyperboles and parabolas as sections. Let's see. By sectioning this surface with the horizontal plane, we obtain curved lines which we verify as being hyperboles. Intersections with right planes will render parabolas. Let's return to those 3 projects, Niemeyer, Gaudí and Candela, and our initial question. So after all, the answer that seemed apparent wasn't. The 3 buildings are in fact curved surfaces. True. But in history, we have just witnessed that these curved surfaces in particular are ruled. They are surfaces capable of being generated by lines. In architecture, shapes, geometry and formulas entwine naturally from the idea to the construction. Mathematics is not an abstraction disconnected from reality, but a vehicle of the project. The creative design needs shape and rule. It needs a language that can provide its representation, calculation and execution. It needs geometry and equations. And now why don't we go and have a look at the Geometria Intuitiva and Interactiva at gi2.pt and learn from these and other interactive models and games.